Hello everyone, my name is Priyanka. Today I'll talk about paper number 14, which is on the complexity of deciding soundness of acyclic workflow nets. So let's start with this seminar. Initially, I will talk about Petri nets and workflow nets, as a workflow net is a subset of Petri net. What is the difference between two? In this paper, the author has improved result from previous research and proved the result or the complexity of soundness of one bounded acyclic workflow net is co-NP complete. Earlier it was co-NP hard, and in this paper it has refined the previous results. For the both this problem, the improved results has been shown. Also, finally we will see the future work and we will conclude the seminar. So let's start with the introduction part. Before I start with the introduction part, if you know the soundness properties and the complexity theory, then this seminar will be easy for you. So let's start with the Petri nets. Petri net was invented by Carl Adam Petri in the 60s. This is basically a tool for modeling and analyzing dynamic aspects of business processes. The business processes can be insurance claim approval or approving a loan in the bank. Petri net is a state-based instead of event-based workflow, where workflows are event-based. We will see what is the state-based in next slides. Petri nets has a graphical nature, but also it has a formal semantics. Formal semantics, nothing but the mathematical structure, that is and or are in the workflow nets. So because of this mathematical thing, the ambiguities, uncertainties and contradictions are prevented. There are several analysis techniques and tools available to analyzing these needs. This is a definition of Petri nets. Petri nets are directed weighted bipartite graph. In this example, this is an example of a business process of insurance claim. The places are represented by circles and those are intermediate states. The boxes or the rectangle are the transition. Those are corresponds to the activities or events of process, and the arcs are from places to transition or from transition to places. The weights are associated with each arc. The Petri net are directed weighted bipartite graph. That means the bipartite graph means there are two types of nodes. So in this example, there are two types of nodes, which is a place and a transition. There is an initial marking in the Petri net. The Petri net contain the places contains tokens, that is a black dots. So here initial marking is 300. The claims or the black dots are required to start the business process, and when these tokens have been reached to the ready place, that is the output place, then that means the business process has been finished. The Petri net's notation and terminology. The Petri net is a tuple PTF, where a P is a finite set of places and a T is a finite set of transitions. There is no common node, that is P. The places and transitions are different, and there is an arc from place to transition and transition to place. There is no direct arc from place to place or transition to transition. A directed arc from a place P to a transition T indicates that P is an input place of T. So here input place for T1 is P1 and P2. So that is a preset of T1 is P1 and P2. Next, a directed arc from a transition T to a place P indicates that P is an output place of T. So the post set of T is P, that is post set of T1 is a P3. Let's take an example of Petri net. So this is how Petri net looks. The places, transition and arcs between two. So as you can see, there are four places, that the places, as you know, the places are states, and transitions are transitions are the events. So the three transitions are T1, T2 and T3, and there is an arc from P1 to T1, then T1 to P3. So these are the flow of a Petri net. The T1 has two inputs, P1 and P2, and it has one output, P3. So the preset of T1 is P1 and P2, and the post set of T1 is P3. So this is a basic example of Petri net. So this is required in the next slides. So how the business process starts? When the business process starts when initial input, that is the place, has at least one token. So at least one claim should be there to start a business process. So operational semantics of Petri nets are token, and the distribution of tokens across all places in Petri net is called marking. So here the marking is 1, 2, 0. To start a business process, initial marking should be provided to the Petri net. So here M is a marking and M0 is a initial marking. So here a state is P1 plus 2 P2. So this is a state. As I said, the Petri nets are state based and not event based. Depending upon the states, the Petri net works. A transition T in a Petri net is enabled in a marking F if for each P there is at least one token. So if P2 doesn't have any token, then transition T1 won't be enabled. In this case, the input places of T1 has at least one token, then this T1 is enabled and has been fired. So the transition firing example. So initially the business process insurance claim has three claims, and those are cases. So one case is taken and the transition has taken place as there are at least one token in a place. After the transition, one token is removed from place and placed into another place. So claim, under consideration and ready, these are the states. The record, pay and send letter, those are the transition of Petri nets. So once one case has been in under consideration state, then the transition has taken place depending upon their property. That is, if the claim has been approved, then it has been paid, or if the claim is rejected, then a rejection letter will be sent with the rejection reason. So these are the state before and after the transition record fires. So record is fired and then marking has been changed. Initial marking is 300, now marking is 210, and it is a k bounded, that is the cases has not been incremented automatically. Those are the same even after the transition. Given a Petri net P and initial state M, initial state marking M0, the firing transition has been taken place. So if initial marking is M, then it reaches to M dash if there is a transition T is enabled. Also, if a firing on an enabled transition T has been taken place, then it removes one token from M and places a token in another place. So this is like a firing on an enabled transition T removes token from each input place P and adds to M dash P to each output place P dash. So to move from M to M dash, there could be a sequence, there could be a firing sequence, and also a state M dash, that is a marking M dash, is called reachable from state M if there is a firing sequence that leads from state M to state M dash. Suppose there is state 300 and it reaches to state 210, that means that state is reachable if there is a firing sequence. There are some behavior properties of Petri nets. The first property is reachability. So initial marking is M0 and it is reachable, and there is a marking Mn, then Mn is reachable from M0 if there exists a sequence of firing that transform M0 to Mn. So reachability is decidable but exponential. Another property of Petri net is boundness. The k bounded if the number of tokens in each place doesn't exceed a finite number k for any marking reachable from M0. Suppose there are 3 tokens initially and it does not grow arbitrary while the business process is in process. One bounded net is called safe. A PN is live if every reachable marking enables some transition T. Liveliness is a third property. That means the Petri net is live. That means there are no deadlocks and every marking enables some transition. So there is no inactive part in the Petri net. So let's come to the workflow nets. Workflow nets are subclass of Petri nets. The tasks are represented by transitions, places are represented by conditions, and cases by processes. Those are modeled by tokens. The operational semantic between workflow nets are tokens. Workflow nets are applied to model and analyze many concurrent systems such as workflow management system and web services. So let's come to the notation. A workflow net is a workflow net. A Petri net is a workflow net if and only if there is one source place and there is a one sink place. So that means the source and sink doesn't have any arc incoming or outgoing. The source doesn't have any incoming arc and sink doesn't have any outgoing arc. And all nodes, that is places and transitions, is on the path from input to output. So that is a workflow net. Is soundness property of workflow net is based on these 3 properties, that is option to complete, that given an marking initial marking I from every marking M reachable from I, marking M dash can be reached, that covers O. That is if the business process should start and complete, that is from initial marking M to the last marking M dash. Net is a free of deadlock and infinite loops. The other property is proper completion. There is a proper termination for any case, and if the process has been completed, then at least one token should be present at the output place. When the workflow terminates, no other tasks are still running and termination is signaled only once. No dead task. For every transition T, a marking M reachable from I. So the workflow does not contain any part that can never be activated. So quasi liveliness. So liveliness preserves that there is no deadlock and the business process will complete and there should not be any deadlock in the process. So every transition is enabled. The weak soundness guarantees that the target state is always reachable, but not each task has a chance to be executed. Suppose the Petri net has many tasks and there to reach to output place from input place there are many tasks. So one path is completed and the output place has been reached, but no other task. The remaining tasks are not executed. That means each task has no chance to be executed. In this paper, the author has answered 2 questions. First, is it decidable whether a workflow net is sound, and if soundness of workflow net is decidable, how complex is to decide it? So first, it has proved that soundness of workflow net is equivalent to boundness and liveliness of Petri nets. As a workflow net is a subset of Petri net, As both properties are decidable, conclude that soundness of workflow net is decidable too. For general Petri nets, boundness can be solved in polynomial time. The liveliness problem is recursively equivalent to the reachability problem. Liveliness is that there is no deadlock, and from input to output the transition has taken place, and finally the target state has been achieved. So liveliness problem is recursively equivalent to the reachability problem. Also, the boundedness can be solved in polynomial time. So we can prove the workflow net is sound and it is a decidable. So if soundness of workflow net is decidable, then how complex is to decide it? So in this paper, the author has proved the complexity of soundness of one bounded acyclic workflow net is co-NP complete, and weak soundness of three bounded acyclic ACWF net is co-NP complete. These are the refined and complete result from the previous research. So first goal is to prove the complexity class to the co-NP complete for the one bounded acyclic workflow net. So how do you do this? So previous result of this problem is soundness problem of one bounded workflow net is p-space complete. Again, this result has been improved and show that this problem belongs to co-NP hard, and in this paper author has improved result again and proved the complexity is co-NP complete. So we will see how he has proved the complexity belongs to the co-NP complete. So let's start with the proof. So one bounded workflow net. So the first part is to prove the membership of soundness to the complexity class co-NP, and then we obtain that soundness problem of one bounded acyclic workflow co-NP complete. So first prove. So these are the basic complexity theory definitions. NP is decision problems decidable in polynomial time by non-deterministic algorithm. Many people have misconception that is decision problem decidable in non-polynomial time is NP problem. It's not like that. It's a decision problem decidable in polynomial time by non-deterministic algorithm. Co-NP problem is a complement of class NP. Similarly, the NP complete problem is when problem is in both NP and NP hard. The decision problem example is satisfiability problem of Boolean formula. As you can see, this is a formula, the Boolean formula, where the conjunction and disjunction of literals has been showed. These are the clauses. So this is a 3CNF form and it is solvable in NP complete complexity, and the complexity of 3DNF is co-NP complete. Related problem to the satisfiability is validity problem, which asks to decide whether a Boolean formula is true under all assignment of Boolean variables. So satisfiability is to evaluate the truth value, is to check if it is satisfiable, if it is evaluated the truth value true, and this is a problem which asks to decide whether a Boolean formula is true under all assignments of. So let's start with the proof. The proof is to prove that it belongs to the co-NP class. They have given a non-deterministic algorithm for the non-soundness of acyclic workflow net. So input is acyclic workflow net and the output is yes if the workflow net is not sound and no otherwise. So the soundness property is equivalent to boundness and the liveliness. So if there is a deadlock, then it will output as yes, that means it is a non-sound. Also, this is a property of liveliness, and other property of soundness is boundness. So non-deterministically the workflow net select a marking M. Suppose M is reachable from MI, but from M the output marking is not reachable, then it is not sound. So in this case, this algorithm outputs yes and otherwise no. So in polynomial time, this can be proved. The reachability problem of acyclic Petri net is NP complete. So non-soundness problem is no NP complete. So the soundness problem of acyclic workflow net is in co-NP. So hence we have proved the soundness problem of acyclic workflow net is in co-NP. Also, the 3 validity problem reduced in polynomial time to the soundness problem of one bounded acyclic workflow net. So idea behind it, how do we prove it is co-NP complete? So it can be proved with the reduction theorem. So the 3 value problem reduced in polynomial time to the soundness problem of one bounded acyclic workflow net. As we know, the 3 value problem is co-NP complete. If we reduce it to the one bounded acyclic workflow net, then it could be also in co-NP complete. So by combining results of part 1 and part 2, we can prove that this problem belongs to the co-NP complete. For example, if no transition has been enabled, then we cannot reach to the output marking MO. That means it makes this formula false, and if this formula is false, then this is not satisfiable and not sound. If the transitions are enabled and we reach to the marking MO, that means it is satisfiable and we can reach to output and the workflow net is sound. So by combining and reducing the problem to the one bounded acyclic workflow net, we can show the soundness problem of one bounded acyclic workflow net is co-NP complete. Next goal is to prove the weak soundness problem of 3 bounded acyclic ACWF net is co-NP complete. Previously, author has been proved that the problem belongs to co-NP hard, and again we have to improve the complexity to the co-NP complete. So how do we do it? First, we have to prove that problem belongs to co-NP, and it has already been proved that it is in co-NP hard. Then we can say that it belongs to co-NP complete. As you can see here, if problem is in co-NP and co-NP hard, then the decision problem can be in co-NP complete. So the first part, the weak soundness problem of acyclic workflow net is in co-NP. This has been proved in previous slides. Next, we just have to check if it is in co-NP hard. So free choice net. So here it is a 3 bounded ACWF net. So what is the ACWF net? ACWF net is a asymmetric choice workflow net, which is a generalization of free choice nets. So free choice nets are a marking that will enable all other transitions sharing an input plus T. That means if a marking that enables a transition, suppose a T1. So for the free choice nets, let's take an example. Here T1 is a transition and it has an input P2, and this input has been shared by T2. Then a marking that enables a transition T will enable all other transitions sharing an input place with T. So T1 and T2 are enabled. When only T1 has been enabled, it also enables the T2. Asymmetric choice workflow nets, as I said, it is a generalization of free choice nets. If two places have same common output transitions, then one of them has all the output transitions of the other. Suppose P1 and P2 both have transition T1 in common, then one of them has all the output transition of the other, then P2 will have the transitions of other, that is P2 will have T1 and T2. A cyclicity in the workflow net is that there is no sequence in the workflow net, that is no arc from P1 to T1, T1 to P3 and again to P1. So there is a cycle, so it is avoided. So the acyclicity must be preserved in the ACWF acyclic net. Let's come to the proving part. So here the weak soundness problem of 3 bounded acyclic ACWF net is co-NP hard. So how do we prove it? Suppose here I is the input place, O is the output place, and there are transitions and places between I and O. For each class there is a place, and as it is a 3 bounded, each place can have maximum 3 tokens. To each variable xi there are 4 places, there are 4 transitions, as you can see tx1, tx1, and there is a negation of the transition variable. Places gets marked when the transitions are enabled, and finally token is O is inserted in the output place. If C is satisfiable, then workflow is not weakly sound. Suppose we reached the output with at least 1 token, then it is satisfiable, then this is not weakly sound. If there is at least 1 place SCJ not marked, then this T will never fire. So in that case C is not satisfiable, so this is a weakly sound problem. So we understood that not satisfiable clause proves that the workflow net is weakly sound. So if the idea behind is to prove it is co-NP hard is to reduced to the new problem, that is if any instance of complement of 3 satisfiability can be reduced in polynomial time to an instance of the weak soundness problem of 3 bounded acyclic workflow nets, that means satisfiability problem is in NP complete, is co-NP complete, is NP complete, and the complement of 3 satisfiability is co-NP complete. So if we reduced this problem to the 3 bounded acyclic workflow net, then we can say that 3 bounded acyclic workflow net is a co-NP complete. So combining these results, finally we have proved this problem belongs to the co-NP complete. In this paper we have seen how author has improved the results and proved that both these problems belongs to the co-NP complete, and the future work in this paper is the complexity of weak soundness of 1 or 2 bounded acyclic ACWF nets remains an interesting open problem. Thank you for listening.